Hey everybody, welcome to A.R.E Live. I'm Mark Tier, the founder of Black Spectacles, and today's episode features Mike Newman answering questions from our audience. Some of the questions that Mike discusses include how the different exams bleed into each other, how to handle the architecture history questions that are scattered throughout the exams, and the differences between some of the key structural formulas. Now before we get started, if you'd like to attend our next A.R.E Live broadcast, visit blackspectacles.com/podcast to register. And during the broadcast, you'll have a chance to ask questions and share your answers with Mike. And if you don't know Mike, he is an adjunct professor at the School of the Art Institute of Chicago. He's also the founder of Shed Studio, and he is the instructor for Black Spectacles' online AIA A.R.E prep curriculum. If you haven't already checked out our AIA A.R.E prep curriculum, head over to blackspectacles.com to watch any of the free tutorials from the courses. And today we have two very special Black Spectacles promo codes to share, so make sure you stick around until the end of today's episode. But first, let's hand it over to Mike.
Hello, everybody. We got kind of a random array of questions, and we'll go through them just one by one. And I'll try to treat them just as sort of both specific, but also talk a little generally about the issues surrounding these topics. A couple of the things are a little on the complicated or open-ended side. So I'm going to talk about them in a way that I think fits to the exam. But then we'll try to provide some links later on that you can link to sort of more specific information that's a little hard to do in this kind of context. So I say, let's just dive right in. There we go. Okay. The first question that came through was, could you talk a little bit about panel points for joists and trusses? So panel points are kind of an interesting concept because, well, trusses are an interesting concept, right? If you have a truss, the gist of the idea, sorry, this is the world's worst drawing of a truss, but the gist of the idea is that I have a structural member, and I'm just going to talk about trusses in terms of beams for now. I find that when you're talking about these topics, it's easier to think about it in beam form than getting into all the other complications, and we can talk about it more generally that way. So the whole point of any sort of type of beam really is span. And to get span, what we really want is depth. That's what you're really looking for when you're trying to get span. That's how you get stiffness. That's how you get the capacity to span longer distances. And so while thinner, less depth material can span pretty far, depending on if it's steel or if it's certain kinds of wood, the game is always, can I get more depth compared to the amount of weight of steel, or compared to the amount of like how big a tree would I need, et cetera, to get it to have more depth. And so the truss is the way that you get that. And the trusses can span anywhere from like a floor truss for like a wood frame house. You might use a floor truss made out of 2x4s, where each of the members is made out of a 2x4, and that might span anywhere from say 18 feet to 26 feet or 30 feet even, all the way up to really giant steel trusses that, or concrete trusses that can span hundreds of feet. So the idea of the truss is a very flexible, used in all kinds of different settings. But the gist of it is I'm looking for as much depth as I can get for the amount of material that we're using. And it's broken up into these triangles because the whole point of the truss is that the triangles are the most solid of the shapes. The triangle can't be broken down. So as each piece tries to be sort of pushed over, the triangular shape can't. It can't deform into anything else. The only way that the triangle can deform is by the members, the actual lines that make up the triangle. Those can break or deform, but the triangle shape itself can't. So the truss is always a series of triangles. And with the truss, any one of these pieces, the whole point is that any one of these pieces is actually a relatively small member. And so I have small members at the on the inside in what's referred to as the web members, and small members at the top and the bottom, which are the chord members. And by putting these all together in these triangular shapes, which can't deflect easily, can't deform easily, allows us to span really pretty impressive distances with very, very small individual members, because they are now made to become one very deep member. So when you start to think about that, you realize that any one of these moments, as I said, like let's say the top chord there, that top chord in a wood truss for a house, like I said, could easily be a 2x4 on its side. Well, if I started to put a giant load directly onto that 2x4, that 2x4 is going to start having its own set of problems, right? It's not going to be that the overall truss is now loaded. The question will be, can that 2x4 hold that particular load? Let's say it was a giant air conditioning unit or something like that. So what I want to do, if I can, is instead of putting a load just kind of randomly located on the truss, I want to put a load right where some of these pieces are. Sorry. So I'm going to have that load. In this case, I'm hanging one. Maybe here I'm loading from the top and coming right down. And you'll see that I'm pointing directly at where these different members, the web members and the chord members, come together. Those are the panel points. The reason they're called panels is because each of the triangles is called a panel. So they're talking about the nodes where these things come together. They'll also be referred to as nodes. But panel point is specific in referencing the place to load. So the point of that is that each of these members, as they come together, the web pieces and the chords, the top and the bottom chords, are connected in pin joints. So the forces will always be sort of thrust straight through all of those lines of those webs and on the chords. There's no moments set up in the individual pieces. That's why they can all function so lightly and so simply. And so the forces, when you load directly onto a panel point, will create a situation where the force is equally spread through the whole thing and is not then reliant on the strength of the individual member. So that individual top or bottom chord can be a much lighter member because you're not trying to load directly onto that. You're loading on the overall member, and you know that because you're loading the panel point. You're loading the spot that allows it to spread that load through the top chord, through the web members that come to that node, and then eventually to the bottom chord that is also connected to those web members. And so it spreads that load through the whole system in the way that it's meant to be spread. So that idea of the panel point is really just that the whole point of the truss is to use very, very light members as much as you can, but get a lot of depth out of the overall truss, and therefore making sure that you don't accidentally load that truss in a way where the individual tiny member breaks, therefore making the whole big member not function. You don't want the whole truss to fail because you put the load for the air conditioner, or not air compressor or something, onto that wrong part of that truss. So trusses are incredibly simple idea, but you have to use them carefully because that if you load them incorrectly, they will fail dramatically. Now, obviously, there's a lot of different versions of trusses. There's sloping trusses. There's scissor trusses. There's a whole series of different types of trusses. There's a lot of online material showing you different examples. The concept holds true no matter what. You're always loading at the point where those loads can be spread to the other members and not where any one individual portion is taking the whole load. One little caveat to all of this, this is sort of what I always refer to as the architect's truss, is the idea of the Vierendeel truss, which I'm going to draw another terrible truss here. Vierendeel truss looks like this. I'm sure you've seen it, that those are supposed to be straight lines and perpendicular lines. The Vierendeel truss is not a truss, but it's called a truss for some historical reason that I have no idea why. In this case, each of these nodes is actually a moment connection, and the diagonal pieces in the triangles are gone, which is why it's not actually a truss. The reason I mention it is that you still call these panel points, and there's still a reason why you might want to load on those direct panel points, having to do with spreading the overall load. But the main reason I mention it is that whenever you talk about trusses, the Vierendeel truss is one of those weird ones that has a very specific name, and therefore you can often get a question about it. It's worth kind of just knowing what it is, but also knowing that it's not a real truss, right? Pretty much all the other trusses, you'll still follow all of the same basic, whether the top chord and the bottom chord are parallel, doesn't really matter as long as there are triangles, as long as the overall system is made out of hinge pin joints, and as long as the loading is done on the panel points, that's all still considered a truss no matter what the shape is. Okay, this is another structural one, and this one and the next one I'm going to talk about pretty generally, and then, as I said earlier, we'll have a link to get a little more specific information on. And there's a couple of reasons why I'm going to talk about these generally, but load reductions and the codes. The thing about load reductions, the term load reductions, is that it actually has a huge number of meanings. There are many ways that term will show up in code material and also on the exam, some of which are just sort of anecdotal or just sort of ways of describing something. You're just talking about there's a load and you're reducing the load, and so it comes across sounding like a load reduction. Other ways are specific things you're allowed to reduce the load demand for when you're doing a set of calculations. And that will come for a number of different reasons. Before I talk about that for a second, though, let me just say that there are a couple different ways that you can think about this. So load reductions can happen because of the type of load it is. So for example, snow loads or wind loads are sometimes treated differently from other loads, seismic loads. It can happen, you can get a reduction in the required load because of the location of the member that you're trying to understand. So we'll talk about that in a second, but like the specifics of that particular spot on the structure may be such that you are allowed to not consider the full expected load because it's just not likely to happen. And then the other sort of factor in all of this is going to be the material of the structural system and the pattern that structural system is being put together. So for example, you'll have different versions of load reductions for wood structures than you will for steel structures or for concrete structures. And a concrete slab, flat slab, would have a different set of load reduction factors than, say, a one-way joist system in concrete. So the specifics of all of those factors will play into the system of load reduction. So a couple of different ways to think about this. Like some people will say, well, wait, why can we reduce the load at all? Like, isn't the load the load? But if you actually start thinking about it, you realize, well, actually, no, the loads are really just sort of an idea, right? Some of the loads are very clear and direct. Those would mostly be the dead loads. And so the dead loads on a structure are the things that are part of the structure, that are always going to be there. So if I have a steel beam and a steel joist system with a deck and some concrete on top of that, I can actually calculate out what all of that weighs, and then that is my dead load. And that means that the structure has to be able to, first of all, carry all the dead load. It has to be able to hold itself up. And then there's the live load, right? And the live load is all the other stuff. It's us, it's the people who are walking around, it's the furniture that's movable, it's the snow that arrives, it's all of the different things that are changing all the time. So the dead load, relatively simple and straightforward and actually kind of calculable. Not always, there's some examples where it's harder to do than it sounds, but you can kind of you can generalize into saying that the dead load is relatively easy to calculate. But the live loads, actually, there's a whole series of different live loads that are all over the place. So where do we get live loads? Well, generally we get live loads from codes where they say, all right, in an office setting, we're going to say that's 100 PSF, 100 pounds per square foot of live load throughout this structure because of the type of use that structure is. So it's this idea that is given to you that this is a code-generated element. Now, you don't always have to use the code. You can actually do, in most situations, you can do calculations based on reasonable estimations, and then provide that to the code officials, and they'll accept it or not accept it. But typically, you just take those numbers out of the code, and they're over the years, reasonable, safe numbers that pretty much will encapsulate everything. Every once in a while, you get a live load that's a little higher than what's put into that number, but typically the loads are a little bit lower than that. And so it's just a way for us to be able to make decisions. We need some weight, some load in order to be able to do the calculations. So by doing all these calculations, you suddenly realize, well, really, I'm going to have exactly 100 PSF over the entire surface of the floor area? And when you really start getting into it, it becomes kind of clear that, well, that's actually kind of unlikely. And so there are ways to start thinking about, well, okay, there's a series of expectations, but then the particular elements, you can start to reduce the robustness of those particular structural elements, like say a girder or something, because you know that the likelihood of it being fully loaded all the time is just so unlikely. So that's one reason why you're allowed to do certain kinds of load reductions in certain kinds of settings. Another reason that you're often allowed to do load reduction is the idea of, if you think about sort of difference between a tributary area and a sort of it's referred to as the area of influence. So for example, if I have a girder and a girder, and I have a series of beams, and then there's flooring on top of those beams. If I was looking at this particular girder, and I was looking at the tributary area, well, I'd go halfway, right? I'd draw a line halfway and halfway, and this area would be the area that would be considered the tributary area for calculating the size of that. But in fact, there's another girder over here, and there's another one down there, and these beams are connected, and they're all stiffened because they're all working together. And so there's an influence area that is much larger, essentially twice the size, because I'm including the influence of this girder and these beams all the way across. And so that's another example of certain kinds of settings that you are sort of allowed that, yes, the loading is done in this very particular way, but we also know that there's a whole series of these things over and over again, and they influence each other in their strength capacity and can spread loads in sort of in ways so we can reduce the size of the members because we know that they're all going to work together. So that's another sort of way of thinking about it. Sometimes there's elements that's different for, say, multiple story than it is for a single story structure. You'll see those kinds of issues. So there's a whole bunch of these different issues that have to do, that the codes will actually write out and you can put into your calculations that, all right, given this position in this setting with this kind of load and with this structural material, each one of those gets a factor, and we can reduce the size of the member by essentially increasing the allowable load that we can put on that member. So this is, like I say, there's a lot of parts there, which is why I think showing a link will be more useful down the road. But the thing to take away is these are the ability to say within a given setup, it has to do either with the material and the layout, or it has to do with the type of loading, like say snow versus wind versus seismic, something like that, or it has to do with the material, the location itself of the individual member. all of these different factors can play into the idea of a load reduction. And it's built into the codes so that you don't have to make things that are killer robust all the time, because it's just sort of a waste of energy and materials. There are a few places where no matter what, you're always doing the full-on thing. And this is actually kind of an important point from an exam standpoint. If you can totally imagine a question that says, so what load reduction can I use when I'm doing an assembly space? And the answer is none. If I'm doing an assembly space or a high importance area, which is usually referred to as type A, I believe. So something like a hospital or a police station, or something that really you absolutely want to withstand a hurricane or something like that. Those areas, you're not allowed to use any of the load reductions. So there are places where they're allowed and there are places where they're not allowed. Certain things like if you're doing a calculation with seismic loading and you also have to include the wind loading, the sort of expectation is, well, yes, one could have a seismic event at exactly the same time that a tornado is going through, but really it's kind of unlikely. And so you're allowed to kind of reduce one compared with the other to make sure that the building is safe, but also reducing the load that you're supplying when you're combining these things together. Another example would be snow and seismic and some other ones like that, same kinds of ideas. So there's a lot of different parts to it. The gist of it is there's sort of realities of building. The code live load numbers are built on a sort of general, simple idea that says this is one size fits all. And then in order to deal with that, they provide all these different ways for you to reduce those numbers in a way that's specific to logical ways of reduction, so you're not making anything unsafe. A little complicated. It's actually a very simple idea, but all you really need to know is the simple part, but you should understand some of those different breakdowns. Let's try the next one. Next one's gonna be kind of similar. ASD versus LFRD. This question is essentially about how we calculate the size and the robustness of the structural elements that we're working on. So, what do we need to have the structure hold together? And at the same time, we're trying to provide a kind of a reasonable factor of safety. So it's not just that the structure is going to stand up, but that we're providing this extra factor of safety, so that if things are built a little off, or if over a span of time something rots out or rusts or something, like we have some ability, a little bit of extra in there in order to make sure that things stay safe over time. Plus, there's always the issue of how people actually use the building, the space, the structure. We build it in one way with one set of codes, but then things change and people have parties in warehouses or whatever, and there's dancing and the floor structure is getting a different load altogether. So the question is, well, okay, how do we calculate not only knowing the capacity of the material, say steel or concrete or something, but also how do we calculate this knowing that we have to add this factor of safety and be sort of extra careful in order to make things be safe down the road. So the ASD is the allowable stress design, is kind of the old school way of thinking about this. The LFRD, the load factor and resistance design, which I always mess up on, but I think I got right this time, load factor and resistance design, is kind of the more modern way of thinking about it. And the gist here is that these are both just ways of assembling the calculations. There's no real major difference in the outcomes. It's just two different ways of getting to the same idea. So with ASD, with allowable stress design, so any of you went to had structures, a few years back, you probably all know the steel handbook, and that steel handbook, in the old green one is the old ASD, They've now sort of switched it over. The 13th edition of the AISC, I think it's called, has sort of kind of complicated this question a little bit by changing ASD to sort of match a little more closely with LFRD. So the question actually gets really, really complicated when you start getting into all the specifics. But at base root, it's actually very simple. So here's the deal. The ASD, the sort of old school version of this, is we have a series of loads. We calculate what those loads are. That would be both dead loads and live loads. We add them up, and then we say, okay, we're going to do this out of steel or out of whatever, let's say steel, and we want to know how big a member we need, how big a beam we need in order to be able to accommodate this load. But before we actually do that, we're going to add the factor of safety. And so there's a bunch of ways that you get to that, but typically what it really boils down to is that you're going to take that load, the dead load and the live load, you're going to multiply it by 1.6. And that 0.6 is the factor of safety. So the ASD says, all right, figure out all the, get all the numbers, calculate everything all the way out. And then once I've calculated all the way out, I then just multiply it by this big number at the end. And that takes it and makes it a much bigger number. Then we go in and we look at the capacity of the steel, and we say, all right, this one, does this steel beam meet this this larger stress? And so what we're essentially doing is we're taking there's the actual stress, that the capacity of the steel, and then there's the allowable stress. And by having this factor of safety in there, that's how we've included that. We've made that difference to what they're going to allow us to use using ASD. And we can then choose a beam that fits that, and there you go, it's all done. We can do that same thing with columns, and we can do with purlins and floor structures, and et cetera, et cetera. It works all the way through. It gets a little more complicated than that. That's why I said this is just sort of the overall piece. But that's how the simple idea is. You put all those things together, and then we give it a factor of safety, and then we look it up, and we make sure that the beam that we're going to use can not only fulfill the need, but fulfill the need with that factor of safety. LFRD is saying, like, they were sort of looking at it and they were saying, well, wait a minute. We're going to treat the dead load the same as the live load. Here's a situation where the dead load, we know really well what's going to happen with the dead load, right? I mean, there's a set, the steel isn't going to change weight. The concrete isn't going to be different, 10 years from now as it is right now. Like, we know what the load is on that. So we don't really need to be so dramatic about, oh, we're just going to multiply that by 1.6. But the live load has some serious question mark to it. So that probably does make sense to have that big factor of safety on it. So if the dead load has a factor of safety of 1.2, and then the live load has a factor of safety of the 1.6, you can see that very quickly that's going to be a different allowable stress than the ASD was giving us, which was multiplying everything by that 1.6. So you might say, oh, okay, that means the ASD is always going to be more conservative than the LFRD. Well, no, because there's another couple of factors that go into the LFRD, which is they then start adding factors in that have to do with the kinds of loads that you're factoring in for. So just as an example, if I have a very abrupt load, I would have to add more. I'd have to add to the total load more because I'd be worried about it just collapsing under a very abrupt loading. So like a truck suddenly driving on something, or a puncture load from a machine, or any sort of abrupt loading. Whereas ductile loading, things that sort of happen over a span of time and have the ability to sort of sag before they fail and things like that, I can be less concerned about adding more factors of safety on there. So I'm going to have a series of factors of safety that I'm just going to keep adding up and adding up and adding up. So it's going to start lower than the ASD, but it may actually become more conservative depending on the specific of the situation. In a fairly simple, standard, straightforward setting, when your factor of safeties are roughly in the kind of 1 to 3 ratio, it's the LFRD is going to give you slightly smaller members. You're going to be able to use less material. In other scenarios, you can actually come up with, if for some reason I had a very, very heavy dead load, for whatever reason, you can actually get a situation where the ASD actually is easier to deal with, and less conservative. So there's not a right and a wrong ASD and LFRD. If you actually go through on most settings, you'll have essentially the same structural choices. It just might be slightly different, and I might be able to save a little bit of material, especially for steel, and be able to reduce the size a bit, and therefore save money and save energy and save sustainability issues and all of that. So if I don't need to do it the ASD way, the LFRD, the idea is that, well, we can find one that's more nuanced and more specific to that particular load by combining all of these different loading factors. And that's the gist of the difference. They are just ways of calculating the allowable stress and therefore being able to choose a specific loaded member. So beams, say, for example, it's just a way to choose a beam. One is a little simpler, one is a little more complicated. The little more complicated one has a little more nuance, is a little more specific. As I said, the 13th edition of the steel manual has actually kind of made this even more complicated because it's actually started to change the ASD so that it's more like the LFRD. I don't really understand why that's happening, but whatever. The gist of it is that's all you really need to know. Any of the questions now, I would imagine they still have some leftover questions that use ASD that are still sort of floating in the system. But in general, any of the new questions will be based on the LFRD. And so the calculations are those calculations. So in other words, you'll see the ones that have all these different factors all tied into it. And the tables are the tables specifically for the LFRD. But it's essentially the same thing, just these two different ways of approaching it. Like I said, we'll try to find a good, little bit more descriptive with maybe some samples and make a link to that. All right, this one, the question was, I've had questions that seem pretty off topic, such as BCDS material choices and SPD distances on the PPP exam. So programming, planning, and practice exam, having questions on it that really ought to be on the site planning design exam or the construction and the construction systems. So any suggestions on how to prepare for this kind of, I used cross-contamination while preparing for one particular exam. So the simple answer to this is no, because who knows what the heck they're gonna throw your way. But I will say a couple of sort of general ideas about how to think about this. For one, the best way of preparing for any of the exams is to take any of the exams. You start to get an idea of what kinds of ways that they ask questions. You get a feel for what they include in their sort of purview. And so taking any of the exams is always a good idea just to get a couple under your belt. But there's also a few that are kind of grouped together. The two that are sort of obviously grouped together, and I would definitely consider taking at roughly the same time, would be the SPD and the PPP. So site planning and design and the programming, planning, and practice. In certain ways, the BCDS can also have some of those questions, especially as regards geotech information and foundation systems and that kind of thing, which definitely applies to SPD and to the programming, planning, and practice. And also the construction documents and services exam can have similar kind of overlap. There's a lot of stuff in construction documents and services about, say, surveys or that kind of information. And the reason is because surveys are a legal part of the process, right? They kind of fall into the construction documents, into the kind of legal understanding of who does what and how these things all fit together, and who orders the survey and all of that kind of stuff, which is the owner, by the way. So there are reasons why those questions fall into those locations, but they also could fall into the site planning or into programming planning and practice. So I always suggest that you actually kind of logically group together a few of those exams and study for them in a kind of a larger grouping. So don't think of program planning and practice and site planning design as totally separate entities, and I'm going to do one in December and I'm going to do the other one in July. Instead do them one in July and one in August or something, where you spend June kind of thinking about both of them, then you get very specific about one of them, and then once you've taken that one, get specific again. But it allows you to sort of think of them all in these groupings together. The other one that's kind of along those lines, you can sometimes find that there are aspects of the building design and construction systems has a lot of relationship to the building systems, because they both start putting in these very kind of real world sets of questions that are talking about specific buildings and material choices and specific things. So you can easily have a conversation, say, just as an example, about R values under systems, because they relate to heating systems and all of that, air conditioning systems, but they also relate to the materiality and the design, the detailing, so that relates to the building design and construction. So these things kind of logically fit together, and so there's logic to why one exam could have these slippage questions that come from these other topics. So the gist of it is, don't worry about it too much, because it's just going to happen and there's no way you're going to be able to judge it, and you're not going to be able to guess what it's going to be. But the other is, just think about them logically together. Don't just randomly jump from one to the next. Have a system for how you're going to do these things together, and then they'll start reinforcing each other. Is there a particular one that is like absolutely like the best one to start with and the best one to end with, or anything like that? No, right now you just find your own path. The one caveat to that is, and there's a bunch of other material, we have another version of this, one of these episodes available to you that talks about the changeover from A.R.E 4.0 to A.R.E 5.0. And there are some reasons why you might want to choose certain of the exam topics first, because they'll be easier if you get a few of those done. They'll be easier to then translate into 5.0 if for some reason it takes you a while to get through all the exams. You should be able to do, if you're listening to this, you should be able to do the exams under 4.0. You have plenty of time left. But when it comes to the changeover to 5.0, that might be an issue. So there are two reasons why you might be grouping things together. One is for that transition, and the other is that, for example, site design and PPP kind of want to be grouped together. So think about how you make your schedule, think about how you move through the process, and kind of think in that way. The other thing to say is just remember that, like, what the point of each of these exams are. So when you talk about site planning, right, the issue is that you kind of what are all the factors involved in how you would make a set of decisions about where things go? Where does the building go? Where does the patio go? Where does the plaza go? Where does the parking go? And those elements can be based on all kinds of things. They could be based on zoning issues. They could be based on can the soil react well to putting a building here? Does the septic system logically go into one location versus another location? And how does that push the building around, right? Well, those could easily be in a couple of different settings. So you have to kind of think about it in that way and be open to those different possibilities. Otherwise, you get lost in kind of this silo effect of, oh, I'm only thinking about this issue. Well, none of the exams are going to be like that. They're all going to be going crossing across a bunch of different exam lines. So I think I managed to not answer that question pretty well. I'm going to move on. Okay, this one is another kind of similar question. Regarding the random architecture and planning history questions, is there any suggestion on how to deal with those? Like, what do you study and what do you focus on? My suggestion on the history and the planning history questions, the architecture history and planning history questions, is that you just get some very simple, straightforward, you probably have one sitting around from an architecture history class, but just a simple textbook. There's a bunch of any of the sources, the Ballast and the Kaplans and those sorts of things have a lot of sort of very simple and straightforward sources. We have some on some of our videos that talk about these issues. That what you want to figure out is, like, they're not going to ask you general questions about architecture history or planning history that are just things that you would need to have to know, right? They're going to ask you questions that are specific to the exam topic. So, like, nobody cares if you know, what would be a good example? The year that Mies van der Rohe died, doesn't matter. But you should know that Mies van der Rohe focused on steel structures. Like, you can very quickly and clearly identify him in a very particular way. So that if there's a history question while you're taking the structures exam, and the question includes Mies or includes steel, and Mies is one of the answers, well, he's sort of iconic and representative of steel. He's probably the answer, right? If you're talking about concrete, it might be Calatrava or Nervi or somebody along those lines. So what you're looking for when you're doing the studying, you don't need to study everything. You're looking for the iconic ones that are easy to ask a question about. They're not trying to figure out if you are potentially an architectural historian. They actually don't care about that. What they do care about is that you have some idea of the kind of these main turning points where specific people or specific planning concepts happened in order to because those were kind of turning points in how we think of the kind of precedents in architecture. So from a planning standpoint, a couple of the ones that jump to mind are things like the Garden City movement that came from out of the UK around the turn of the last century. The new urbanist stuff that came sort of to fore in the 80s and 90s here in the States and spread around. These are kind of turning point elements that kind of captured an imagination. Those are kind of key and important to be able to respond to, but the questions won't be complicated. They shouldn't be, at least. What the questions should be based on is just sort of that you understand that as a precedent, that you understand that this was a key moment in time where this thing happened. And then there's some kind of deeper historical things, like you should understand the difference between a Renaissance city and a medieval city, right? That there's sort of these patterns that aren't random, that they have to do with very specific moments in time. Nobody's really going to ask you, well, what year was Venice laid out, anything like that. But you should understand the relationships of kind of big pictures of how those things go. So I would get one of those textbooks, but don't read it. Just flip through, find the key spots, look for names that you recognize, read up a little bit about it, and just kind of move through and make sure you understand the key elements that bring you to these like turning points. It's hard to think of one in wood, but there's a few different, as I said, Mies, there's a few other steel people, there's a couple of concrete ones, there's a series of planning ones. You might have some kind of modernist things that will talk about how modernist planning versus traditional planning. It'll only be ones that really sort of captured a moment in time, and that's what you're really focusing on. So I wouldn't fret about it. The way the history questions got in there is, in the old days, there was an actual history exam. It was actually a whole separate exam, and you had to take a whole exam on architecture history. And then my guess is that people kept failing it, and so they decided to get rid of that, and they just spread the questions about through all the other exams. So the history questions will be on topic to that exam. So it's like maybe you might have what would you have in systems? In systems, you might have kind of a question about people using solar power or something like that, when did that happen? How did that happen? In structures, as I talked about, people using specific materials. In programming, planning, and practice, it might be about kind of what are the precedents, sort of, as I said, these different systems for organizing, like medieval versus Renaissance versus modernist. Like how would that play and what would those precedents be and why might you choose those in any one situation? So it'll always be specific to that exam, but it could be about any of those different people, but it won't be completely random. It won't be unknowable. It's something you can actually study for fairly simply. I would spend maybe 2 days on it and then you're probably good to go. All right, let's move to the next one. On the site planning vignette, can the plaza or garden be any crazy shape as long as it is within the required square footage and meets all of the required adjacencies? And then another question, is it possible to put in too many trees to screen wind and views on the site planning vignette? And does the service road have to be in a very particular relationship to the building? On this first part, the plaza can in fact be essentially any shape. The giant caveat to that, though, is that if the plaza gets too thin, I'm not sure how the computer reads it. I'm not sure if it reads it less as not as a plaza, but as a walkway, and therefore falls into a different category. So I would try your darndest to make it a reasonable shape of a plaza. There's no reason why you can't be sort of fluid with it, but it's just hard to know exactly what the parameters are specifically. Like if you get it down to say 5 feet wide, my guess is that the computer looks at that and says, that's not a plaza, that's a sidewalk. So I would just be careful about that kind of thing. But if it's a Z shape in some way or something along those lines, or big L, that's all fine as long as you're meeting all those other issues, square footages and the adjacencies. And even the square footages, you have a 10% play, which is actually quite a lot. I wouldn't be overly concerned about it, but you do want to make sure that it is reasonably close to the required amounts. The other reason to try to keep it as straightforward as you can is just in general, the simpler your plan is, the easier it's going to be on you while you're doing it. If you can keep it fairly simple and straightforward, a simple rectangle, a simple maybe L with a small leg or something, it's just going to be more straightforward for you while you're doing it. It's easier for your brain to understand that it's there and the scale of it and what can go up next to it. And also, if you have to change something down the road later, the more crazy that plaza is, it's just harder to make it work. If you have to change one thing, now I have to really think about all the different shapes, possibilities. Whereas if I start with something that's nice and simple and straightforward, if I have to then push it around a little bit and make it a little crazy, that's okay. So that's what I would say about that, is try to keep it as straightforward as you can, but you actually do have quite a bit of flexibility on it. The second part, is it possible to put in too many trees to screen wind and views? The answer to that is yes and no. The reason no is no, you can put in as many trees as you want. The reason to say yes is that the more trees you put in, first of all, you're sort of going beyond what you need to do. All you really need to do is just show that you understand the idea that certain kinds of trees, which, think about it, which trees? If you're trying to block wind and views, those can't be deciduous trees, those have to be coniferous trees, right? Because they have to be down low where you want to block the view and the wind. So you have to choose the right kind of tree. And if you're trying to block a wind pattern, if you put, say, 3 trees 15 feet apart from each other, and then 2 trees set back from those in the void spaces between them, that's those 5 trees are going to block any wind conceptually that we want to get into. So what I was saying there is, if I do 3 trees and then I do 2 more, right? Any wind, if the wind is coming this way, and I have my plaza or something here, that's fine. You don't need to do 100 trees. And if you do 100 trees, you're likely to put a tree someplace that causes a problem. You're likely to put a tree in a place you're not allowed to put it, or it's going to be you're going to have to move the road for some reason that you didn't expect, and now you're cutting out a tree. If I put a tree in and then I kill it, it's just like I'm killing a tree that was already there. So don't overdo it, just put in what you need. Something like I just sketched is more than enough. You could probably just do the 3, but that's plenty. And then does the service road have to be 20 feet perpendicular to the building, or can it run parallel? I'm not actually 100% sure about this one. I do know that the best scenario is that it's perpendicular, but my guess is that it can also be parallel. But what I would look for is a specific wording in the code, because it could actually be different on different exams. And that it would have to tell you that it had to be perpendicular in this kind of setting. So if the road has to be coming perpendicular off of, if this is now our building, it has to be coming perpendicular, it'll say something in the code requirements. But I do believe you can have it come up parallel, but the perpendicular is definitely the preferred choice. All right, let's try the next one. Stair and ramp vignettes. The width of the stair as it relates to the area of rescue, and the width of the ramp at 180-degree turn versus a 90-degree turn. So the width of the stair as it relates to the area of rescue is truly weird. So you're going to have to read very closely on the code for the stair vignette. So you calculate out the total occupancy load, right? You're sort of looking for how many total people. So we're looking for the occupancy of each floor. And then you're going to divide that by however many stairs there are, any exits are, which is either going to be 2 or 3. So I'm going to take that occupancy and I'm going to cut it. Let's say I have an occupancy of 320. Well, I'm going to cut that in half, and because I have 2 stairs, and so now I have 160. So I now have to make sure I go through the numbers and I say, all right, 160, what kind of width do I have? I'm going to go through that whole set of calculations. And often those calculations will end up being, the load will end up being smaller than the minimum width. And so the minimum width will be actually the width that you're using often. Sometimes with minimum width typically is 44 inches. Sometimes it'll be up to 48 inches, sometimes it'll go up to about 60 inches. It's pretty rare that you're going to get a situation on the exam where it would be bigger than 60 inches. That's a pretty particular situation. You start getting into complications of having to add center railings. People have told me that they've seen that, but it just seems unlikely. I don't think it would happen very often. It seems very unlikely to me. So your range is really between 44 and 56, 60, somewhere in that range. So imagine you have it as that you're only required, say, 36, but the minimum is 44. So you say, okay, we bump it up to the 44. And then on the second floor or on the mid floor, I have an area of refuge. There's a little caveat in the code. I don't know if it's always there, but it is in all the examples that I've seen. A little caveat in the code that says, if there is an area of refuge, then the minimum from that point down the stair is 48 inches. And the reasoning on that is that in our very high-tech world, the very clever, smartest way we've ever come up with of dealing with somebody in a panic, in a fire, in a wheelchair, is they go into the protected stair, because the whole stairwell is supposed to be protected in some level. They go into the protected stair and they wait in the area of refuge until some burly fireman comes in and carries them down the stairs, which seems crazy in its low-techness. But that's as good as we've ever come up with. So the idea of having it that extra size, that extra width from the area of refuge down is just to give an opportunity for the firefighter to be able to physically carry somebody down while somebody else is going up and down. So it's a strange little caveat, and it has a couple of odd little bits to it. For one example, the handrails for the minimum width stair, let's say 44-inch, the handrails are allowed to be actually inside that. There's a certain limit to the distance, so you don't want to do it too far in, but let's say you put them in where they're 3 inches in, something like that. That gives you a little bit of room for your hand to be able to grab the handrail, and it kind of comes into the space.
We do have 2 questions. Are the codes provided in the program tips for the stair ramp vignettes, or is that knowledge you need to know going into the exam? Same thing for stairs and handrails.
That's a great question. There are certain things you should just sort of know how to do. You should have had some practice. You should have done a stair or 2 in your lifetime to sort of be able to do these vignettes. But it's actually the only things they can really test you on are the codes that are given in the vignette. All of that code will come in the vignette. And the reason for that is, you can't, the Chicago code, for example, has, even though it's now based on International Building Code, has a different railing height in certain scenarios than other codes do. It can't be that they would be so specific that you would have to know that. So they give you all the information that you have to deal with, but you have to read it very carefully to try to understand it, because it's worded a little oddly. So let me just get back to the thing about the handrails being able to be within the width. So that means the handrails, the width of the stair is the 44 inches, but the handrails are within that. On the 48-inch one, from the area of refuge down, that's actually not true. It's actually from handrail to handrail. So it's you have to be very specifically reading through that. Once you've read it a few times and once you've practiced it, it actually comes through very simply. And that particular code item may not be there on the one that you're working with. So you want to know how that you practice them, test them out, try to get to know them, but be willing to go back in so you know what the code is going to be before you even start the vignette, but then go read it again anyway, because there could very well be something that's a little different, and they might have a slightly different way that they word it, and you want to pick up on those changes. It'll probably be the one that you've practiced on, so it's probably not a big deal. So that's the weirdest thing about that, and then from there, that 48-inch would go all the way down. If your width was, say, 56 inches or 60 inches already because of the calculations, then it wouldn't affect it, because you're already more than that 48-inch. All right, now regarding the ramps, the big thing on the ramps is that if I have a ramp that's coming and it has a minimum width of, let's say, 48 inches, so the width across is 48 inches, and then I have another portion of that ramp is going right there, and that's also got that same minimum. I can't just have these meet in a straight corner, because I actually need to have a 5x5 space for the turnaround. So I get this kind of funky little extra corner built in there. And what the exam allows, because part of the point of the exam is, can you figure this stuff out in an economical way? What the exam allows you to do is to say, all right, well, that's a little crazy. Why don't we just have it be 5 feet wide? Sorry about my not straight line. I wonder if I can do that again here. There we go. So this is, I'm wasting space on the extra width of the ramp, but I'm also making it much simpler to build elements. Just that one corner instead of this first example, which had 3 corners. And those corners are all very expensive for the railings and for all the little knee walls and curbs and everything. So you will often see that people will suggest that you do, for a 90-degree turn, that you do something like that. If I'm doing a switchback, I lose the advantage. So on a switchback, I'm going to have a situation where I'm coming, say, up that ramp and continuing up that way. This dimension is going to still be that 5 feet, but the width of the ramp can be whatever the minimum is, because I'm not getting that same clean line thing out of that I'm getting here. If I just do the 5 foot fully here, it doesn't get me anything. In fact, is a little wasteful. So the idea that I'm coming around that ramp and I'm keeping with the minimums on the width, but then I'm making sure that I have at least that 5 foot dimension there, so I still have that 5 foot circle capacity on that landing. That's sort of the difference between doing a 180 versus a 90-degree turn. Now, the caveat to all of this is that I can't create a situation where, or I shouldn't want to create a situation where I go from a 5 foot width to a 48-inch width to a 5 foot width to a 48-inch width, because it just gets goofy, and when you're doing egress work, it should always be that it is continuous as much as possible. So hopefully that was clear, but the idea is that it's different on a 90-degree turn than it is on a 180-degree turn. I think we just ran through all of our questions. Thanks for sending those questions in. Those are really some good ones, and like I said, we'll put a couple links in for some of those structural ones specifically.
Okay, John's asking, how do you spell the name of that unique truss that you mentioned earlier?
Oh God, I knew you were going to ask that. Virendil, I have no idea. It starts with a V. Let's see if we can do a quick Google saves the day once again. Yeah. And like I said, it's sort of a goofy one. The reason that I mention it at all is because they always are looking for things that are kind of snappy that they can ask a question about. And Virendil truss, it's just like it has a name, right? It's this very specific concept. You should probably know the component parts of trusses, like a king post and all of those things, but maybe know a few of the key ones, like a how versus a king truss, scissor truss, some of those kinds of things. But you're not really expected to know like all the different names of all the different truss types. But just Virendil is one of those weird ones that it's just likely to come up. I remember I think this is beyond the statute of limitations on these things, so I think I could say it. When I took the exam, however many gazillion years ago it was, I actually had a question about Virendil trusses, and many people have mentioned it to me. So that's the only reason I mention it. So they won't put another V-named truss in the state. They won't try to trick you. It's just whether you would recognize it or not.
Okay. So with that, we'll go ahead and close up today's session. Actually, we did get one more question. So
one slid in. Okay.
Right at the last second here. Structural systems is a discrete topic, straightforward to study for. I hear CDS is similar, not so broad. Others are very wide-ranging. Maybe it's better to take these early on before others. Is Ben's question?
So that's a good question. There really is no right answer to any of this. I think it's important that you come up with a strategy. And I've talked a little bit about a couple strategies, and I'll mention a couple more. What your suggestion is actually makes sense to me. But just come up with a strategy so that you kind of know what's coming. You don't want to be sitting there going, oh, what am I going to take next? You just want to have an idea. And so then lay out your strategy and just do it. By far, the best way you can study for the exam is by taking the exams. And yes, I know you can you can take an exam before you're really ready and not pass. But you'll be ready to take it the next time, and it'll be much better. You'll be much better at it. So I wouldn't get overly fretting about it. Previously, what I would always say is that the best ones to do first, that the absolute first one is you do the one that you are most worried about. The absolute first one, you do the one that you most think you're going to be good at. And that way you kind of go in, you start one off, you get one under your belt that you feel comfortable in, you learn like where you park, and you learn where you put your coat, and it's on one that you're not super worked up over. So you start with that one, and then the second one you do is the one that you're most worried about, which for most people is structures. And then you get that one out of the way. Now that you've sort of gone through one, you have an idea of how it's going to work. And the advantage of that is that you have to wait a period of time before you can retake the exam. And that way, that period of time can go by while you're taking other exams. Now, recently they've changed it. It used to be you had to wait at least 6 months. It's now down to, I think it's either 2 months or 60 days or something like that. So it's a much shorter period of time. So that doesn't really matter as much, but it's still not a bad way to approach it, where you say, okay, I'm going to start with the easy one, and then I'm going to dive in on the hard ones, just to kind of get the full range and so you feel comfortable. Having said that, one of the things I remember, it's kind of funny to say now, I actually teach systems, but when I was taking the exam, I didn't know anything about systems. And I went into that exam, I was totally unprepared, and I thought, oh my God, this is going to be a disaster. I hadn't had a chance really to study for it. It's like, oh, this is going to be terrible. And I passed it, and I later, got kind of interested and started studying up on it and got pretty good at it. But like, I passed it before I knew really anything about it. Like, you'll be surprised, even ones you think are hard, you may do just fine on. And occasionally what will happen is you'll get an exam of something that you are totally killer knowledgeable on, and you'll get a bunch of random questions that you just don't happen to know, and you won't pass it. Like, so don't overly fret about it. Come up with a strategy that works and then kind of move with it. I do like the one that you suggested, though. That does actually make some sense. Those kind of more standalone-y ones, kind of get those out of the way and then group the other ones. That kind of dovetails with what I was saying earlier.
So we have a couple other ones here. Michael and Ed are both asking about the construction documents exam. Michael is asking, or really sort of for confirmation, that he should focus on studying the A101, B101, and B201. And then Ed is wondering...
A201, yeah.
Ed is wondering if there's a specific exam that makes sense to combine with CDNS. In your mind.
Yeah, I mean, if I was going to do CDNS together with some other ones, I would do it with site planning and design and programming, planning, and practice. And part of the reason for that is due to the transition to 5.0. There's just a logic to it. But it is kind of standalone. There are parts of CDNS that can show up on any of the exams, and any of the exams can show up on CDNS because the construction documents and services talks about the legal structure around stuff. So that can be implicated in material questions. It can be implicated in design questions. It can be implicated in all kinds of different ways. The CDNS will also talk about like how you structure an office or how you structure a set of documents. So if I'm talking about how I structure a set of documents, well, clearly that's going to be similar in conversation to building design and construction systems. So there are similarities through a lot of these different ones. But just to kind of get back to the initial question that you asked, which ones, what would I focus on? I would absolutely focus on the A101 owner contractor contract, the B101 owner architect contract, and then the A201 general conditions. Those are the three documents that are like by far the most meaningful, that most questions will come from. And you should have sort of a general gist of an idea about what the other contracts are. You don't have to like memorize any of them or anything like that, but you should have a gist of how those things work. So CMs are for construction managers, Cs are for consultants, Gs are like payouts and things like that. You should sort of have an idea of where those other ones are. But the ones that I would actually read through and really try to get to know are the A101, the B101, and the A201. Now, one of the things you will find, I'll just say very quickly, is that if you start at the beginning and start reading, you will be asleep by page 2, and you will have read through the whole thing and not taken anything in. Find a way to read it, like ask yourself some questions and then find the answers in the contract. Or there's a couple of great things on the AIA website. There's a commentary which takes it and breaks down only a few of them for some reason, but it will break down the contract into individual lines, and then there's a commentary with each line. So like, this says this, but what it means is this. And like, find those ways where you're not just like absorbing the words, but not the understanding. You've got to find a way to actually read it for real. It's much harder to do than it sounds. But once you do that, they actually make interesting sense, and you will understand your role in all of this world much, much better the better you understand those contracts. I can't tell you how great it is to understand what those contracts say, because it affects like how long you spend on things, what you say to who, who answers a question in the client meeting, all of those things actually get answered in those contracts, and they're really useful.
Ben is asking if you agree that it's good to group the structural systems exam with the building design and construction.
There is a lot of overlap. I think that's not a bad choice. But like I say, whatever strategy you come up with, there's going to be pluses and minuses to any of them. But there's a logic to that. I would agree.
All right, well, thanks, Mike. And thanks to all of you who've tuned in. If you'd like to attend our next A.R.E. live broadcast, visit blackspectacles.com/podcast to register to attend. You'll have a chance to ask questions and share your answers with Mike for live feedback during that broadcast. And to learn more about our AIA A.R.E. prep curriculum, go to blackspectacles.com. We'll also put a link in the show notes. And for those of you who want to get busy preparing for the A.R.E., you can use a 15% coupon off the first charge of any AIA A.R.E. prep membership with code 52715webinar, which will expire on June 15th. And of course, if you're already an AIA member, you can visit aia.org/ARE prep to get a 30% discount for the entire duration of your AIA A.R.E. prep membership, not just the first charge. This also expires on June 15th. And finally, please leave a comment below the video to let us know what you think and share any suggestions you may have. I promise we'll read every word that you write and use them to tune our next episodes. So thanks for watching.